Let's talk a little bit more about conductors, and in terms of Gauss's law. So remember, conductors in electrostatic equilibrium, which means once the charges have all stopped moving, okay? Where do charges go on a conductor? Like if you have a net charge on a conductor, where does it hang out? On the surface, right? It's the middle school dance model of electrical charge, right? The charges all repel each other. They try to get as far away from each other, and that means they all back up until they hit the wall, okay? So any charge resides on the surface. So if you have a shape like this, your charge is all going to be here, okay? So let's think about this in terms of Gauss's law. What's Gauss's law going to tell us? Let's say we take we create a Gaussian surface inside of this conductor, right? So like one like right here. Let's say you put a little sphere right here. What's that going to tell you about your flux? So what's charge enclosed if you're inside? There's no charge in the middle, right? Because where did we say all the charge is?
Surface.
On the surface, okay? So if you do Gauss's law in here, what's your electric field going to be? 0, okay? So remember, electric field inside a conductor is always 0, okay? The electric field inside a conductor is always 0. So since all charge resides on a surface for a conductor, we know no charge can be enclosed if you create a Gaussian surface inside the conductor, okay? So the electric field is solid everywhere inside the conductor, whether the conductor is hollow or solid, all right? So inside a conductor, you're always going to have an electric field of 0. If the conductor is isolated and carries a charge, the charge resides on its surface, and the electric field of a point just outside a charged conductor is perpendicular to the surface of the conductor, and you can sort of estimate it to be like a plane, okay? Because all the charge is on the surface, that means the outside surface of a conductor is like a charged plane. So it's going to have a similar electric field outside to the infinite plane. So it's going to look something like this. Okay? Some charge density divided by epsilon naught.
So is this guy a 2-dimensional shape or 3-dimensional?
Technically it's a 3-dimensional shape, but it's hard to draw.
So if you're gonna look at it 2-dimensionally and you shaved off just the top of it, there would be charges in that middle section because it's the surface.
Yeah, if you cut this part off,
yeah,
you take some charge with you.
Okay.
But yeah, and then the charges would redistribute to the new surfaces.
Okay.
Yeah. Okay. So the electric field at the surface is perpendicular to the surface. So if you wanted to draw the electric field, right, there is an electric field from this thing, and it's going to be perpendicular to the surface. Okay? And near the surface, it's going to be approximately charge density divided by epsilon naught. So something similar to a plane. Okay? All right. So let's talk about, the other thing to remember is when you're talking about conductors, if it's a sphere or something, basically just a sphere, the charge is going to distribute really evenly. But what if you have a shape that's not even? What if you have a pyramid? What does the charge do then? So it turns out the charge goes to the pointier parts. Okay? So if you have a conductor, let's say you have something that looks like this. And this is a conductor. If it has a net charge, you'll have quite a bit of charge up here. You'll have some charge down here at these corners, and then you'll have a few little charges spread out in between. Okay? So if you have a nice smooth surface, the charge distributes smoothly. But if it's not smooth, then it concentrates in the pointy parts. Yes.
Is that because the sides are closer to each other there?
Kind of. It's complicated because it's really just saying that, they're repelling, but if you have, like the radius, if the radius of curvature is smaller, the charge just kind of gets like stuck there. Like it can't repel as easily because, I don't know. Without like showing you with math, it's kind of hard to describe why it does that, but you can just remember that for conductors, the pointier parts have more charge, okay? But yeah, it has to do with like, to solve it, you have to set it up as an energy minimization problem, and you have to like integrate it, but the end result's the same. Charge goes to the pointy parts, okay? All right, so let's talk about conductors in an electrostatic equilibrium. So let's say this is a sphere. This is like a cantaloupe with the middle scooped out, okay? So we're just looking at the cross section. But this is like a round hole. This whole thing is a sphere. Okay, so we're just looking at it as a cross section because what we're going to do is we're going to start by putting a little negative charge in here. Okay, so if we put a negative charge in here, what do we know about the electric field inside a conductor? It has to be 0. Okay, so what do we know about what should happen to the charge on this surface? Let's say this is a negative 1 coulomb.
Mm-hmm.
What should the total charge on this surface be?
1
1 coulomb, right? Because in order to get electric field 0 here, the charge enclosed, when you draw a Gaussian surface, is going to have to be 0. So if you have a negative charge here, it's going to attract some positive charges, and they should add up to the same charge as this, just with an opposite sign. Okay, well let's say this was a neutral conductor to begin with. So let's say before we even put any of this stuff here, this conductor had 0 net charge. Okay, it has positive and negative charges, but it has them in equal amounts. So once we put this negative charge here, we end up with positive charges here. How do we maintain the same net charge? What other charges, how else does the charge redistribute?
Negatives go outward.
You have negatives go out, and what should they add up to? If this is negative 1 coulomb, this is 1 coulomb.
0.
Now what's the net charge going to be on the outside?
Oh, equal to the same as positive.
Negative 1. Yeah, negative 1. Because, remember, these charges plus these charges have to add up to 0, because we said originally the net charge was 0. Okay? So there's a couple rules here. One, the net charge on the conductor has to add up to whatever your net charge is. So if you start with a neutral conductor, then if you put 5 coulombs here, then this has to be negative 5 coulombs. Okay? If you put 2 coulombs here, this has to be negative 2 coulombs. But what if your conductor already had a charge? What if it starts with plus 2? Then what does this plus this have to add up to?
Just 2.
Plus 2. Okay, so that's the idea. We have some rules, right? Inside the conductor, electric field has to be 0. So these things have to cancel. All right? These things don't have to necessarily cancel. They have to add up to the net charge. Okay, so anyway, we have negative Q inside the conductor, right? The inner surface has charge Q. The outer surface has charge negative Q. All right? Let's say we have negative 3Q inside a conductor with charge 4Q. Okay? So this is negative 3Q. What's this?
Plus 3.
Plus 3. What's the outside going to be?
Plus 1.
Plus 1. Why?
Net charge is plus
Has
4.
to add up to 4. Okay? And the other rule is still that all the charge ends up on the surface. So whether it's positive or negative charge, it ends up on the surface. So if you're going to, let's say we wanted to do this as a Gauss's Law problem. Okay? So I'll draw it over here, and it's tricky. So this is the conductor. plus 3q, or minus 3q in here. Okay, then out here, on this surface, we have plus 3q, and then on this surface, we have plus q. Okay, so let's call this radius A and this radius B. Let's say we want to know the electric field everywhere in space using Gauss's law. Okay, so we'll start with R less than or equal to A. Okay, so that's inside here. So we draw a little Gaussian surface. Make it yellow. There's our little Gaussian sphere inside A. All right, so we have E dot dA equal to Q enclosed over epsilon naught. All right. We know because the sphere, there's symmetry, this goes away, we end up with E times dA as an integral. What's the area, what's dA going to give us? It's a sphere.
Yeah,
4 pi little r squared. Okay. On this side, what's Q?
Rho.
No, what's Q?
negative 3.
Negative 3Q. Okay, that's this. Over epsilon naught. Okay. So electric field inside the sphere is going to be negative 3Q 4 pi epsilon naught. And 1. Sorry, made that messy. So 1 over 4 pi epsilon naught negative 3Q over r squared. So k negative k 3Q over r squared. And what does this look like? We look at the relationship between E and R.
It's the equation for
Yeah, it's a point charge, right? So even if none of this other crap existed, it doesn't even care that we're inside the conductor, right? Because we're not in the conductor, we're in the hollow space inside the conductor. All it cares about is the charge enclosed, which is just a point charge, okay? So we have our electric field for a point charge. Then let's say we do R greater than A but less than B. So that's in here. Okay, so this is our new R. Once again, when we do Gauss's law, we end up with E. This side should be the same, 4 pi R squared. What's the charge enclosed?
1.
So this is minus 3Q.
Should be 0.
Plus 3Q is 0. That means our electric field is 0, which is what we would expect because we are inside a conductor. Okay? At this radius, we are inside the conductor. Inside the conductor, hollow or not hollow, the electric field is 0. Yes?
Then what's that divot if that's not inside the conductor?
With what?
That,
Inside this,
yeah, why is that not 0?
you have to be in the metal. This is the hollow space inside the metal.
Okay.
So if you're, what I mean by inside the conductor is like physically inside the conductor, like you're inside the metal.
Okay.
Yeah. So even if you have like so if this charge wasn't here, this would be 0 too. Okay, but if you put a charge inside the hollow, empty space inside a conductor, then you'll have a field just from that charge.
Okay.
Okay. And then the last one is R greater than or equal to B. So that's out here. So, once again, E dot dA, so that's going to be E times 4 pi r squared. You'll notice the left side of the equation is always the same. Okay, as long as you're using a sphere, it should look the same. The range of r changes, but that's it. What's the charge enclosed when you're outside?
1
Net charge.
Yeah, 1, right? Because you have minus 3q plus 3q, that's 0, plus 1q, that's going to be plus q over epsilon naught. So this is going to give you kq over r squared. Yeah. So it looks like a point charge. Okay, but it looks like a different, the scale of the point charge has to do with how you add up these charges. Okay? So how do we feel about that? Conductors are a little more straightforward, but you have to do the accounting of these charges. So if you have a net charge on the conductor, the surface charges on the conductor have to add up to that net charge. And if you're inside the conductor, the charges inside your Gaussian surface have to add up to 0 because we know the electric field inside a conductor is 0. So the nice thing about the conductor problems is if you're inside the conductor, you don't really have to do any math, you just know it's 0.
So now we're going to have to start doing 3 of these for every problem instead of 2.
Wait, what?
Now we're going to have to start doing 3 of these for every problem instead of 2.
Oh, I mean, you can do this with an insulator too. It's just a horrible pain in the ass. And you know, definitely test fodder, right? Because if you have a sphere with a hole in it, calculating the volume gets really interesting, right? Because you have to do the big volume minus the small volume, and it's not too hard once you get the hang of it, but you end up doing a lot of algebra.
Okay, so we're going to try this problem out, and we have this neutral metal sphere of radius 5 centimeters. It has a hole at the center with a radius of 1 centimeter, and at the center of the hole you have a charge of 2 nanocoulombs. We want to figure out the surface charge densities, and I'm also going to actually do this problem as a Gauss's law problem just for practice since we haven't done one with a conductor yet. So I'll go through that after we figure out the surface charge densities. So this is just sort of a step more than what we were doing in the last couple example problems. So let me first draw this sphere. And obviously it's hard to draw three-dimensional things. So I'm going to draw it as a circle, but you'll have to realize that it's actually a full sphere. And then make one of these white. This is not drawn to scale, but you get the idea. Okay, so here's our sphere. Let me just make this like a slightly lighter gray. And this is a hole in the middle. Okay, so this is sort of like the cantaloupe model. So it's really just a sphere with a hole in the middle sort of carved out of it. And in the very center, we have this +2 nanocoulomb charge. Oops. Okay, so if the thing at the center is +2 nanocoulombs, then the charge at this inner surface should be -2 nanocoulombs. The other thing is we know that the charge of this whole thing is 0. Okay, so that's what neutral means. It means, so neutral sphere. Metal says conductor. Neutral says that the charge is 0, so Q equals 0 inside the sphere. Actually, let me do that with black so you can see inside the sphere. Which means that if there's -2 on the inside, whatever this is plus whatever's on the outside has to add up to 0. So the charge on the outside should be +2 nanocoulomb. Oh, okay, weird. Okay, just can't use the highlighter on this one. So, so basically, just to remind you, the inner charge actually covers all of the scooped out part of the hole, but for some reason my highlighter's not working, so I can't draw that. So it's not just spread out over the circle, it's spread out over the whole scooped out inside. And also the +2 on the outside is sort of spread out over a whole sphere. So imagine sort of smearing it over a basketball or a baseball or something. Or a cantaloupe, because we already used that as an example. Okay, so in order to calculate the surface charge densities, and this is important because we're calculating surface charge densities, remember we know that surface charge density is Q, total charge, over total area. That's just the definition of surface charge density. So for the inner, right, that means we want Q in over 4 pi r in squared. And so we know this is r in and this is r out for inner and outer. Let me just sort of, so for r in, let's make that pink, right? That's this. And we know that the inner radius is 1 centimeter. Okay. So in order to do that, we just plug in our values. So we know this is -2 nanocoulombs, but you want to write that as times 10 to the -9th coulombs divided by 4 pi times 0.01 meters squared, and that gives us an inner value of -1.59 times 10 to the -6 coulombs over meter squared. Now, because we know the inner and outer charges are the same, which density do you expect to be bigger? It's got to be the inner one, because you have the same charge spread out over a smaller sphere surface. So the inner one's going to be a bigger density, more dense, right? Do the same thing, Q out over 4 pi r out squared. That's going to give us +2 times 10 to the -9th coulombs. That's this surface charge. And then we have 4 pi times 0.05 meters squared. So plugging that in, you should get something smaller. That's going to be 6.63, 6.37 times 10 to the -8th coulombs per meter squared. And so obviously 10 to the -8, much smaller than 10 to the -6, and that's what we were expecting. So that puts us in the right range, okay? So that's our surface charge density, which is cool, but we actually really want to, figure out Gauss's law for these things. Oh, look, I found the highlighter does work. It's just hidden from us. That's neat. Okay. Very annoying. Okay. Thanks, Notability. So if we want to calculate the Gauss's law stuff, I'm going to do this fast just because it's an extra example. We start with Gauss's law. And so we'll start by calculating Gauss's law. Oh, it wants to erase it. Cool. Gauss's law right here. So we'll call this R. So R less than R in, that's going to be, this is a sphere, so E times 4 pi R squared, right? That's the surface area of a sphere. We do the dot product, we get rid of that, all that jazz. Q enclosed is just going to be, let's call this just Q. So let's say Q is equal to plus 2 nanocoulombs. And then that's divided by epsilon naught. So you end up with E is equal to, remember 1 over 4 pi epsilon naught is K. So K Q over R squared, which is just, looks like a point charge. Okay, then if you want to take the electric field here, you don't even have to do Gauss's law, you just know you're inside a conductor. So if R in is less than R is less than R out, so if you're inside the conductor, you can just say E equals 0 because you're in the conductor. The other way you can get that is you know that the net charge enclosed is plus Q minus Q, or plus 2 nanocoulombs minus 2 nanocoulombs, so the net charge part would be 0, and you can get it that way too. So this is for R less than R in. And then if you're out here, and this is your R, you'd say R is greater than R out. Then you have 4 pi R squared, just like here, is equal to, here's plus Q, then you have this surface, which is minus Q, and you have another plus Q out here. So that's going to be Q over epsilon naught, and you end up with E is equal to KQ over R squared, which is the same as what we got for this first part, right? So in these three ranges, you have this, and what this looks like if you plot the graph of electric field versus R is pretty much you have something that's dropping and then goes to 0 for a bit and then continues dropping. So this would be R in, this would be R out, and this would be 0. So looks sort of like this. Okay.
Sort of the last topic in here sort of relates back to the last. So let's say we have a capacitor. What do we know about the electric field inside a capacitor?
It's constant.
Constant, right? So we have this constant electric field inside a capacitor. Let's say we throw a conductor in this electric field, okay? Well, it's a neutral conductor, but of course it still has charge. What's going to happen to the charge?
It's going to repel all the positives and attract all the
Where's the positive charge going to go?
on the right side.
On this side,
Yes.
right? Where's the negative charge going to go?
On the left side.
And that means inside that conductor, right, so all the positive charge goes here, all the negative charge goes here, you can now draw an electric field that goes the other way, right? Because electric field lines go from positive to negative charges. So we'll draw it like this, okay? And basically it's going to move until it's in equilibrium. And when it's in equilibrium, that means there's going to be no more force on the charges to push them to the other side. So it turns out the electric field inside this thing has to exactly cancel the electric field outside, and you end up with an electric field equal to 0 inside the conductor, and also inside the hole in the conductor. Okay, so this is called electromagnetic shielding. And remember, in the lab, we had a question about this where it was asking, can you shield gravitational fields? And the answer is no, right? Because gravitational fields, unlike electric fields, don't have this sort of binary nature to the sources of the field, okay? So what I mean by that is electric field comes from positive and negative charges. Gravitational fields just come from mass.
Oh, is that how a Faraday cage works?
This is a Faraday cage, yeah.
Ah, that's interesting.
Well,
That's something
so
else.
this is why, for instance, if your car gets struck by lightning, you don't get struck by lightning. Okay, if you're in the car, all the electrical charge just goes around you. All right. Other things that are fair. yeah, so basically if you're completely surrounded by metal, electromagnetic charge, electromagnetic waves can't get to you, okay? Which is why sometimes you have really bad cell service in things like elevators. Okay, all right. Any other questions? Yeah, but we already answered this in the lab, so that's the end of this chapter.